Hello, everyone. We are delighted to present our work entitled Towards Enhancing Database Education, Natural Language Generation Meets Query Execution Plans. I am Saurav, and this is a collaborative work between NTU and CDN University to enhance technological support for database education. Given an SQL query, the query optimizer of a relational database management system generates a query execution plan or QEP, which is then executed by the query engine to retrieve the results of the query. This is a core topic in any database systems course in undergraduate computer science degree programs around the world. I was teaching the database systems course in NTU in 2017. While teaching the topic on query processing and optimization, I had this following interesting conversation with a student that set me thinking on how I can help make his learning journey of QPs easier. The mismatch in QP description in an off-the-shelf DBMS and that described in textbooks and lectures makes it difficult for him or any other student to understand QPs. Although vendor manuals provide details regarding vendor-specific implementation and language, it can be boring and tedious to read, especially when you're a student. This set me thinking. Indeed, if we take a look at the DBMS market landscape in last 10 years, the space has only become more crowded as there are more vendors now compared to 10 years ago. All are jostling for increasing market share. To the best of our knowledge, all these vendors develop DBMS for enterprise customers and pay scant attention to pedagogical support to enhance database education. The key question we focus in this research is whether we can describe a QP using natural language so that it can help learners to understand query execution plans generated by an off-the-shelf RDBMS. Answering to these questions demand juxtaposing ideas that often doesn't go together. The majority of natural language interfaces for RDBMS have focused either on translating natural language sentences to SQL queries or narrating SQL queries in a natural language. Juxtaposing query execution plans and natural language is an idea that often doesn't go together in database research. To the best of our knowledge, there is scant attention to this issue in decades of research on natural language interfaces for RDBMS. So what are the key issues here? If you regard a query execution plan as an input language, while the NL description as the output, then we can view the generation of NL from a QP as a machine translation task. However, addressing this task using deep learning is fraught with challenges. First, deep learning based techniques need massive training sets of labeled examples to learn from. Such training sets in our context are prohibitively expensive to create as they demand database experts to translate thousands of QPs of a wide variety of SQL queries. Even labeling using crowdsourcing is challenging as accurate natural language descriptions demand experts who understand QP. Second, ideally, we would like to generate natural language descriptions of QP using one application-specific dataset, such as movies, and then use it for other applications, such as hospitals. That is, the natural language generation framework should be generalizable. This will significantly reduce the cost of its deployment in different learning institutes and environments where different application-specific examples may be used to teach database systems. In this paper, we propose a novel framework called Lantern to address these challenges. Given a SQL query and its QP, it automatically generates a natural language description of the key steps undertaken by the underlying RDBMS to execute the query. The key ideas is as follows. Instead of mapping an entire QP to its natural language description, we focus on mapping the set of physical operators in an RDBMS to corresponding natural language descriptions, and then stitch them together to generate the description of a specific QP. The rationale behind this strategy is as follows. Any RDBMS implements a small number of physical operators to execute an SQL query. Hence, although there can be numerous QP, they are all built from a small set of physical operators. Consequently, it is more manageable to label these operators and generate a natural language description of any QP from them. This allows us to generalize Lantern to handle any application-specific database, as the relations, attributes, and predicates can simply be used as placeholders in describing a physical operator. Last but not the least, it makes our framework orthogonal to the complexities of SQL queries, as they're all executed by a small set of physical operators. To this end, we propose two variants of Lantern, Rule Lantern and Neural Lantern, which we shall discuss in turn. Rule Lantern is based on rule-based framework. The first question we would like to answer here is, how do we facilitate natural language description specification for physical operator? To this end, we present a flexible declarative framework called Pool. Pool is based on a data model called Poem, which is a simple and flexible graph model where all entities are objects. Each object represents a physical operator of a relational query engine and has a unique object identifier. Objects are either atomic or complex. Atomic objects do not have any outgoing edges, and all objects have a set of attribute value pairs. Specifically, each object is associated with the following attributes: source, name, alias, definition, description, type, condition, and target. Let me elaborate on that. The source refers to the specific relational engine that operator belongs to. The name refers to the name of a physical operator in the source. And the type captures whether it is a unary or binary operator. Alias is an optional alternative name for an operator. The definition attribute stores the definition of an operator. The description attribute stores an NL description of the operation performed by an operator. Note that there can be multiple descriptions for the same operator object. The condition attribute takes the Boolean value to indicate whether a specified condition, for example, join condition, should be appended to the natural language description of an operator. Values of all attributes are taken from the atomic type string. The data definition in Pool allows one to declaratively create physical operator objects associated with a specific RDBMS. An example statement to create hash join operator object in PostgreSQL is shown here. Specifically, the attribute value pairs are declared here by a subject area expert. The physical operators are stored in two relations in Poem store. P operator stores all the attributes associated with an operator. Since an operator can have multiple descriptions, this information is stored in a separate relation PDESC. A key operator in this particular language is compose. It specifies the generation of an NL description template of an operator. It uses the description, type, and condition attributes of operators to generate. For example, this particular compose hash from PG shows an example of compose statement for the hash operator in PostgreSQL. In particular, the compose operator returns a value of type string instead of a poem object. In this case, hash and the placeholder of a relation name. When the list of object names in the compose statement contains more than one operator, it is referred to as auxiliary critical operator pair, which generates the template for the critical operator. For example, here, hash is an auxiliary operator as it's supposed describing the hash join operator, which is the critical operator here. Hence, this statement generates the NL description template of the hash join operator. Observe that the relation placeholders are added based on the value of type. If the type is binary, then we know two relations has to be added. Similarly, the condition template is also appended based on whether the value of condition attribute is true or false. If the value is true, then a condition statement is appended. Otherwise, nothing is appended. We now illustrate the rule lantern algorithm with an example. Consider this SQL query from TPCH. So given an SQL query, it first generates the physical operator tree. Next, it traverses the tree in post-order fashion and generates the rule template for each critical operator by invoking the compose statement. For example, the NL template of hash semi-join operator is shown here. These statements are then stitched together to generate the NL description of the QUP. Note that the placeholder relations, attributes, and conditions are filled up based on the specific SQL query. We observe from our engagement with learners that although Rule Lantern have high accuracy, it makes the description of QUPs monotonous, leading to boredom. In fact, this is consistent with psychology theories that repetition of messages can lead to annoyance and boredom. Students reading this very similar descriptions of QUPs tends to get bored. To address this challenge, we develop a novel deep learning based language generation framework called Neural Lantern that infuses language variability in the generated description by exploiting a group of paraphrasing tools and pre-trained word embeddings. The way we generate the training data is as follows. We adopt Kip et al.'s work to generate a set of SQL queries given a particular schema and database instance. Then we can get a collection of QUPs from these queries. Each QUP is decomposed into a set of acts, each of which corresponds to a set of operators in an operator tree or the subtree of the physical operator tree. So a hash join and hash together forms a particular act. Then for each act, Rule Lantern is used to generate the NL descriptions automatically. After that, we can diversify the text by for each Rule Lantern results, we apply 3 state-of-the-art synonymous sentence generation tools and acquire a set of synonymous sentences. We remove duplicates and manually eliminate any invalid statements. Here is an example of the training data generation process. Reconsider the physical operator tree. Consider the act consisting of hash semi-join and hash operators. Rule Lantern is invoked to generate the corresponding natural language template. Then this is passed to the 3 synonymous sentence generation frameworks to diversify the text. In Neural Lantern, we proposed a model called QUP to SIG for translation. It follows the SIG to SIG structure. The acts collection is composed of a series of acts, each of which is derived from the QUP. So the encoder RNN encodes each word in the act into the corresponding hidden state using an LSTM layer. We use an LSTM decoder with an attention mechanism to let the decoder focus on the relevant portion of the encoder while generating a token. We adopt both static, for example, word to vec and glove, and contextual word embeddings like Elmo and Bert in decoder. Training data, we use our workloads in TPCH and SDSS. Then we apply the trained model on IMDb. Pre-trained word embeddings can reduce the validation set loss while improving validation set accuracy and alleviate the overfitting problem. Please refer to our paper for detailed experiments with this aspect. We have built Lantern on top of PostgreSQL and SQL Server. Our exhaustive experimental study with real learners demonstrates the superiority of Lantern to existing QP formats of commercial RDBMS. Specifically, 43 students enrolled in a database course volunteered for the study. This slide shows the response from learners on the ease of understanding of various QP formats. Observe that both Lantern variants perform superior to existing formats supported by PostgreSQL. We also compare Lantern with a state-of-the-art framework called Neuron. It also generates natural language description of QPs using a rule-based strategy. Specifically, we integrate Rule Lantern and Neural Lantern into a single framework as follows. We track the QP NL description pairs viewed by each participant. By default, the NL description of each physical operator is generated using Rule Lantern. Whenever an operator appeared more than a predefined frequency threshold, in total in different QPs associated with a participant, Neural Lantern is invoked to generate the description for the operator. This slide shows the results of user feedback study on Neuron and Lantern. Note that SDSS on SQL Server is not supported by Neuron as it is tightly integrated with PostgreSQL. The translation rules of various operators of PostgreSQL are hard-coded in Neuron. Consequently, learners who were using SQL Server could not benefit from Neuron, whereas Lantern can be used on any RDBMS. This is why Neuron has poor feedback compared to Lantern. Next, we investigate the impact of boredom. We compare the boredom index for TPCH on PostgreSQL. We presented a set of output generated by each operator in random orders. We asked the subjects to rate the degree of boredom, which is our boredom index. They felt perusing these plans to understand QPs using the Likert scale of 1 to 5. The volunteers found the output of rule-based Neuron more boring than Lantern, as you can see in the table. This is shown consistently in all the different variants of the software we explored. In conclusion, this research presents a domain-oblivious framework called Lantern that generates natural language descriptions of QP to aid learners taking a database systems course. It takes the first concrete step to enhance database education using technology. We advocate that RDBMS needs to break out from the enterprise jar and think how to provide effective pedagogical support to learners. This is more important nowadays as education and training doesn't end at the age of 21 or 22 due to lifelong learning. We need to think how an off-the-shelf RDBMS can support this. For example, how do we facilitate understanding of SQL? How do we let learners converse with the query optimizer? Note that these issues are not limited to only relational database systems. Thank you for your attention.